All right, in this video we're going to look at finding terms of a geometric sequence. And a geometric sequence is one in which each term we get is going to be the result of multiplying or dividing the previous term by a constant number. So with arithmetic sequences, we had to add or subtract the same number to get from one term to the next. With geometric sequences, we're going to multiply or divide by the same number. And that same number is called the common ratio r, which is not zero. So geometric sequences are going to model exponential growth or exponential decay. So they're like exponential functions, much in the same way that arithmetic sequences were like linear ones. So here we have an example of the first four terms of a sequence, 3, 6, 12, and 24. And to get from 3 to 6, we have to multiply by 2. To get from 6 to 12, we have to multiply by 2. And to get from 12 to 24, we have to multiply by 2. So notice the points, if we were to connect them, don't make a straight line. They have this exponential growth curve to them. So each y coordinate is going to be twice the previous one, 3, 6, 12, 24. And this indicates that our common ratio of 2 is going to be the base of the exponential function. To find the y-intercept, just take the first term and divide it by 2, that common ratio, to get 1.5. So 3 divided by 2 is 1.5, much like we added or subtracted the common difference from the first term to get the y-intercept with arithmetic sequences. So our function can be modeled as 1.5 times 2 to the x, or in terms of sequences, a sub n equals 1.5 times 2 to the n for values of n that are greater than or equal to 1. So again, notice that our common ratio is the base of our exponential function, and the y-intercept is what we're multiplying our exponential function by. Now, a key difference between geometric sequences and exponential functions, in addition to the fact that we're only going to plug in integer values, positive integer values in most cases for n, is that with geometric sequences, our base can actually be a negative value. So we could have 1.5 times negative 2 to the n power because we are restricting the domain, so we can get away with that with geometric sequences, unlike with exponential functions. So example 6, we're going to find the eighth term of the geometric sequence. We're going to start, our first term is at negative 4, our common ratio is at negative 2. So if we divide negative 4 by negative 2, we get our y-intercept of 2. And our sequence rule, then, we could use 2 times negative 2 to the n power. So plugging in n equals 8, 2 times negative 2 to the 8th power gives us 512. Part B, we have our first term is 80. Our common ratio is a half. So each new term is half the previous term. Our y-intercept then, excuse me, our y-intercept is 180 divided by a half, which is 160. So with our y-intercept and our common ratio, our sequence rule becomes 160 times 0.5 to the n power. So the eighth term, we just plug in an 8, we get 5/8. Part C, the third term is negative 48. The fifth term is negative 768. So in this one, I haven't given you what the first term is, and I haven't given you what the common ratio is. So we're going to have to find both of them. So if we set up kind of a fill in the blank here, is our first, second, third, this will be our y-intercept, fourth and fifth term. Again, our third term, negative 48, our fifth term, negative 768. Well, to get from the third to the fifth, we have to multiply by r, not once, but twice. So whatever the common ratio is, we take negative 48, multiply it by that ratio once, and then multiply it by that ratio a second time, and our result would be negative 768. So negative 48 times r is going to give us negative 768. Or negative 48 times r squared equals negative 768. Divide both sides by negative 48, we get r squared is 16, which makes r equal to plus or minus 4. Now, in regards to that, either one of these actually, for the value of r, either one of them is legit as an actual ratio here. So to find the first term, we actually would have to multiply by 4. We'll use 4 in this case, but truth be told, we could use negative 4 as well. We'd have to multiply by 4 once, twice, and 3 times to get from our y-intercept to our third term. So uh, a sub 0 times 4 times 4 times 4 is 64 times a sub 0 gives us our third term of negative 48, which means our y-intercept negative 0.75. So we have our y-intercept of negative 0.75 times 4 to the n power, and negative 0.75 times 4 to the 8th power is negative 49,152. Example 6, we have our starting term is 5 and our fourth term is 16.875. So we'd have to go 3 times. We'd have to multiply by r to get from a1 to a4. So 5 times r cubed, that's 5 times r times r times r, equals 16.875. Divide both sides by 5 and then cube root, and we get r equals 1.5. So our starting term is 5, but our y-intercept is 5 divided by 1.5, which is 10 thirds. So we have 10 thirds times 1.5 to the n power. Plug in an 8 for n, and we get 10,935 over 128 for our 8th term. All right, example 7, write an explicit rule for each geometric sequence. We have our 3, 6, 12. Well, we saw this already, but common ratio, just take 6 divided by 3, we get 2. So we have to double each term to get the next term. Y-intercept, 3 divided by 2 is 1.5. So we have 1.5 times 2 to the n power as our explicit rule. Part B, 2, negative 10, 50, negative 250, 1,250, yada, yada, yada. Common ratio is negative 5. So negative 10 divided by 2 is negative 5. Our y-intercept, 2 divided by negative 5, is negative 2/5. So our rule then becomes negative 2/5 times negative 5 to the n power. And that about does it for this video. Thank you for watching, and I'll see you next time.